The next encryption system that we're going to look at is one called Gamal. So before we describe what the Gamal encryption system is like, we're going to go ahead and review the elements of RSA encryption, in particular looking at the security advantages as well as the advantages of having a public key. We're going to try to imagine some other security features that we might implement in a public encryption system. We're going to describe what the Gamal encryption system is, and then we're going to do a sample encryption and decryption. All right, so here are the important general features of RSA. I know we discussed this in the last video, but I want to make sure that these are in the forefront of your mind as we think about how to design Gamal. So the first thing, and this was huge, is it has a public key, which means that it gives information so that everybody can send you a message to anyone with a public key out there. It also has a private key that enables only the person who made the key to easily decrypt the messages. We use the mod operator to enhance security. It makes it harder for a cryptanalyst to analyze the computations. And that is actually part of our public key, if you recall. That's our N. The security depends on difficult computations, and difficult computations not just for a person, but for a computer. And for us in RSA, the difficult computations had to do with factoring numbers. So it depended on being able to find phi of n, and in order to do that, you needed to factor the numbers, but we made it so that it was difficult to do that. And that's what gave us our security, as well as being able to let our n be our public key. And what we're going to do is we're going to try to find another system with similar but not identical features. And one thing I want you to remember before we go in here is this is from one of our last videos having to do with the primitive roots. Remember, if you have a primitive root mod p, that's just a number where if you take all of its powers between g to the 1 and g to the p minus 1, you get all of the numbers 1 through p minus 1. Obviously not in that order, but you get all the numbers eventually. So basically, if you look at powers of g, it gives you all the numbers mod p except for 0. All right, so we look at Gamal encryption. It takes a similar approach to RSA, but not quite the same. There's some important differences. So first of all, one of the similarities is it uses mod. But instead of taking numbers mod 2 primes multiplied together, if you remember our n was equal to p times q, where p and q were primes, we're just going to use it mod p, where p is a prime number. So part of our public key is going to be our prime number p, and all computations are going to be done mod p. Computations for plain text, computations for ciphertext, all done mod p. We're going to have a primitive root mod p, right? So what we're going to do is we're going to find a primitive root mod p, and that's going to be part of our public key as well. So far, public key, we have p, we have a primitive root mod p as well. We have a private key that we want to try to keep secret from anyone because it's going to enable us to actually do our decryption. That's going to be some number x, any number x we choose between 1 and p minus 2. Now what we're going to have to do next is sort of describe a way to hide the private key. If you remember with RSA, the way we hid our private key, our decryption key, was by multiplying those primes together that couldn't be factored so no one could find that multiplicative inverse mod phi of n. Here we're going to actually hide the private key in a slightly more straightforward way. We're just going to take our primitive root g, and we're going to take it to the x power. So we're going to stick that x in the exponent of our primitive root. And so h equals g to the x mod p is going to be part of our public key, right? However, the x itself is private. Now, in principle, all I would have to do to find that x is look at the different powers of g and pick the x that gives me h when I do that, right? However, that may sound easy, but if I choose a really large prime, that's going to be very difficult to do. So it's actually computationally difficult to find x, and that's going to be the key to our security in Gamal encryption. Now, one of the features of Gamal that's a little bit different than RSA is for a given plain text, you can actually have more than one possible ciphertext. So what this is going to do is it gives the sender flexibility in creating ciphertext. And what is the amazing and almost magical part is, no matter how the sender sends that ciphertext, we will always be able to find the plain text from it. And I'll show you how that works once we get to encryption and decryption. All right, so let's show how encryption works. Before I do that, I'm going to give a brief summary of what all the keys are. Now remember, our private key was some number x between 1 and p minus 2. Our public keys, we had 3 of them. We had a prime number p. We had a number g that is a primitive root mod p. And then finally we had that number h that was the one that hid the key. That was where we took g to the x, computed that mod p, and that was the third part of our public key. And the way we express it is we just give it as a triple. The first number in the triple is always the prime p. The second number in the triple is always the primitive root g mod p. And then the final number is going to be the number that hides our private key. That is going to be h, which is g to the x. And those are the ones that we are going to show the entire world. Now let's sort of switch roles. So that right when we were creating that encryption system, we were thinking of it from the perspective of the person who's receiving the messages. Now for encryption, we are going to look at it from the perspective of people who are sending the messages. So those people don't know what X is. So as far as we're concerned for encryption, all we know are P, G, and H. So suppose our plain text is the number P. We're always giving our plain text in numerical form. So the first thing we're going to do as our encryptor, and this is kind of a surprising part, we're just going to choose a random number y between 1 and p minus 2. We're not going to share that with anybody, not even the person we're sending to, okay? So you could think of this as our private encryption key in sending the message. So we're going to take that y and we're going to stick it into the exponent of 2 numbers. So we're going to first of all compute h to the y. And remember, h was just the third number in our key. And we're going to call that number h to the y s just to keep things from getting crazy. Then we're going to put it in the exponent of our primitive root g. So c1 is equal to g to the y. And then finally, we're going to take that s we found in step 2. We're going to multiply it by our plain text, take it mod p, and that's going to be our c2. So our c1 is g to the y mod p, which we get from our y. Our c2 is p times s mod p. Remember, the s we got from our y as well. And those c1 and c2, we're going to put those together in an ordered pair to form our ciphertext. So our ciphertext isn't going to be one number, it's going to be a pair of numbers. The first one being our primitive root to the y power, our second one being p times s, where s is equal to h to the y power. And it seems like we should have to know what y is in order to decrypt this. Turns out we don't. I'll show you why in the next slide. All right, so let's talk about decryption. Now, when we get decryption, now we're looking at it as the receiver of a message, which means that we know what our private key is, but we don't know what our private decryption key is. We don't know what the private encryption key y is. Okay. So here are some facts that we have at our disposal to help us decrypt our message. First of all, remember that c1 is equal to g to the y mod p. And again, I don't know what y is right now. Right? I do know what C1 is, and I do know what G is. But I can't figure out why because, again, computationally very difficult to figure out. And remember also that G is our primitive root, which is public. This is public, so we know what that number is. So for C2, we know that is P times S mod P. Now P is just our plain text, and to remind you, S is equal to H to the Y, and remember H was part of our public key as well, and Y was part of the private encryption key that our sender picked at random. And just to remind you, H was equal to G to the X, so we know how we got H, right? Because we made the encryption system. And just remember, X is the private key that only we know. Nobody else knows. Nobody can use it to decrypt any messages. All right. So we know what C1 is. We know what C2 is. We know what P is, and we know what X is, and what G is. So we have a lot of things that we do know. We don't know why though. Let's see if we can still find our plain text. Now, the only equation that we have right now that involves our plain text is C2 equals P times S mod P. So somehow we want to use that to figure out what our plain text P is. Now we know s is equal to h to the y, so we're just going to go ahead and plug that in. So we get p times h to the y mod p. And remember that h is equal to g to the x mod p. And so we can replace our h with g to the x. Now we have a perfect situation where we can use one of those exponent laws, right? We have g to the x to the y. That is the same as g to the xy. So we multiply that by p. And nice thing about multiplication between x and y is it works the same in both directions. So if we have g to the xy, that is exactly the same as g to the yx. And that might not seem important, except remember, those exponent laws can work in both ways. If we take an exponent to an exponent, that's like multiplying the exponents. But if we're multiplying exponents, that is the exact same thing as taking an exponent to an exponent. So our g to the yx is the same as g to the y all to the power x. And what makes that important is we know what g to the y is. If you look at that first fact that we have up there in those bullets, our first bullet, c1 is equal to g to the y. So g to the y mod p is the same as c1 mod p. And so what we get is c2 is equal to p times c1 to the x mod p. And notice that that equation does not involve y at all. It only involves C2, which we know. It involves C1, which we also know. P, the plain text, we also know. And finally, X we know because that is our private decryption key. So if we then look at the multiplicative inverse, multiplied by the multiplicative inverse on both sides, mod P, that tells us that our plain text P is equal to C2 times the multiplicative inverse of C1 to the X. Which means that as long as we know C1, C2, and X, we can decrypt our message to get our plain text P. Pretty crazy, huh? All right, so let's go on to the next one. We're going to go ahead and do a sample encryption, and then we're going to take the ciphertext from that and do a decryption on that to show you how it gets us back to our original message. So for our encryption system, again, we're going to look at it first from the standpoint of the message receiver. We're going to create the system. We're going to find our key. We're going to pick a prime number. My favorite prime number is 47, so that's going to be my P. We got to pick a primitive root mod 47. Now that is difficult, right? Because in principle, what you would do is you look at a bunch of numbers, look at all their powers from that number to the 1 to that number to the 46, and see if you get all the numbers between 1 and 46. That can get old real quick. So I'm just gonna, for these particular computations, what I'm going to do and what I'm going to encourage you to do is use Wolfram Alpha. And the nice thing about Wolfram Alpha is I can put something in like primitive roots mod 47 and it will spit out an entire list of them. And one of the numbers on that list is 10. And so I choose G equals 10. So again, this is something that I did, and just so that I'm not a jerk and get off easy where you don't, you get to use Wolfram Alpha for those as well. All right, so that's our G equals 10. Let me see. The next thing we have to do is pick a private key between 1 and 45. You can literally choose any number that you want. I'm going to choose 8. All right. And then finally, the last part of the public key. Remember, the last part of the public key is where we hid the key, our private key. Our private key is 8, which we don't want anyone to know about. So we're going to hide it using that primitive root. So we're going to take G to the X, or 10 to the 8 mod 47. And again, that's going to be a nasty computation. That I also use Wolfram Alpha for. If you do 10 to the 8 mod 40, if you just write 10 to the 8 mod 47 on Wolfram Alpha, it will spit out 27 for you. So our public key is 47 as our prime. Our primitive root is 10, and our key hider is 27, and we show that to the world, but we keep the number x equals 8 to ourselves. That is our private decryption key. So now we're going to switch from message receiver to message sender. Our message sender only knows the 47, 10, and 27. We do not know the number 8. So if we're going to encrypt this message using the plain text 29, and again, 29, you can think of it just as a number that represents the text of a plain text message. So first thing we're going to do is choose Y, our private encryption key that we're not going to share with our decrypting friends. And again, you could choose any number between 1 and 45. I'm going to choose 9. Didn't want to choose 8, but didn't want to stray too far. But you could choose literally any number between 1 and 45. So I'm going to compute S, and remember S is h to the y mod p. And remember our h in this case is that 27. That's our last number. Our 47 is our p, our g is 10, and our h is 27. So we're going to do h to the y mod p. That is 27 to the 9 mod 47. And again, I'm going to use Wolfram alpha to do that computation to give us 34. So now that enables us to, now we can go ahead and compute C1, which is g to the y mod p. Our g in this case is 10, our y in this case is 9, that's the private encryption key that we chose, and our p is 47. And again, Wolfram alpha spits out the number 35. And lastly, we compute C2, which is P times S mod P. Our plain text P is 29. Our S, we computed that above, that is 34. And our P is 47. And we end up with the number 46. So our C1 is 35, our C2 is 46, and that's our ciphertext. Okay? Now we're going to run this in reverse. We're going to start with the ciphertext. We're going to start with the same key. Our 47 is our prime, our primitive root is 10, and our key hider, our H, is 27. And then we're going to run the ciphertext 3546, and we're going to run it backwards to get our plain text, which hopefully ends up being 29. Now remember, we have one additional piece of information that our encryptor did not. We know the private key x equals 8. And also recall, with all our complicated exponent computations led us to our plain text being C2 times C1 to the x multiplicative inverse. So, nice thing it is, we know what C2 is, that's 46. We know what C1 is, that's 35. We know what x is, that's 8. And we know how to find multiplicative inverses. Well, we could either use the generalized Euclidean algorithm or, let's face it, I'm going to use Wolfram alpha. All right, so let's go to it. So our C1 is, remember, is 35. That's just, we get that from the ciphertext. That's the first number in the ciphertext. So if we want to take C1 to the x mod p, that is the same as 35 to the 8 mod 47. And again, that's a computation that you can easily do on Wolfram alpha. You just literally write 35 to the 8 mod 47, and it spits out 34. Thank you very much. So that's going to be our... so that's going to be our C1 to the x. Now, we're going to find the multiplicative inverse of C1 to the x, which means we want the multiplicative inverse of 34 mod 47. Now, again, this isn't too bad doing it using the generalized Euclidean algorithm, but it is unpleasant enough that I wanted to do it by using Wolfram alpha. And literally you can write in multiplicative inverse of 34 mod 47, and Wolfram alpha will very reliably send you back what that inverse is, and it turns out to be 18. So we know what C2 is, that's 46. And so and now we know what C1 to the multiplicative inverse of C1 to the x is. So we multiply those together, mod p, to get our plain text. That is 46 times 18 mod p. And you have to check this, and again, I checked this using Wolfram alpha. You end up with 29, which was exactly the message that we started with, the plain text message we started with. Whew. Okay, so now I think you're ready to work on the Gamal encryption on the PDF file included with this video. And as I mentioned before, please use the Wolfram alpha to do the nasty mod and inverse computations. You don't need to do those nasty computations yourself.